Hi everyone and welcome to today's Saturday session with ExamRevision.ie. My name is Anya and I'm going to be taking you through the main areas linked with complex numbers for both the higher level and ordinary level Leaving Cert Maths course. So to start off with then, just a quick note just to say that the complex numbers topic generally appears on paper 1. This topic breakdown list is for higher level students, but it's very similar for ordinary level students. But just to note that for both higher level and ordinary level, complex numbers generally appears on paper 1 of your Leaving Cert. And I suppose, look, now more than ever, I suppose it's very important to be aware of the different topics that are going to appear on paper 1 and paper 2, particularly with the choice that we are going to be having on the 2022 paper. So I suppose when you are doing your revision, it is worthwhile to think about which paper it appears on, and then I suppose you can early start thinking, right, if I'm going to be able to leave out one question, is there a particular topic that I'm going to be kind of looking to leave out, or is there more so just going in on the day and saying, right, what question do I think I'm going to find the most difficult? So they're just little questions that you can start asking yourself now over the next couple of months when you are revising the different topics from the course. Okay, so if we just start off by looking at the breakdown of the topics on the Leaving Cert higher level paper 1. Okay, so again, this is for higher level students and I'll show you ordinary level now in a second. So just to draw your attention to the fact that complex numbers, remember, if I just break the paper up into the section A and section B, so we can see complex numbers came up last year as a full question. In section A, the year before, it came up as part of a question. The year before that, its own question. So you can see that every year for the last, whatever that is, 7 years, we've had complex numbers appearing in some shape or form in section A, and that's where you're going to expect to see it. So again, if you are starting to kind of, I suppose, plan out what you may or may not do in your exam, you can see that complex numbers is pretty much a guaranteed question for section A, and it would be certainly one that I would be encouraging you to prepare for, because the questions themselves, you can see, you can go back through them, are very manageable, and I think if you know your key parts of the course on complex numbers, you should be able to give these questions a really good go. And then if we move on to look at the ordinary level breakdown, so for you guys, you can see very similar idea that it comes up quite a lot in section A. So again, section A is up to question 6, and very nicely you can see that it has come up nearly in the same spot every single year. So it's certainly a little bit more predictable for ordinary level students. So again, it's definitely something to prepare going into your Leaving Cert. It came up as question 2 in 2016 as well. So yeah, I would certainly be saying that's a question you can have prepared and have gone through the last number of years, because particularly for ordinary level, the questions are very, very similar. So it would certainly be one that I would be saying to focus on for paper 1. So before I start talking you through what actually is on the syllabus for Leaving Cert higher level and ordinary level maths on complex numbers, I just wanted to take a second to just reflect and say, okay, are we happy that we know what a complex number actually is? So to recap, a complex number is a number in the form a plus bi. And what that actually stands for then is A is the real part of our complex number, and B is the imaginary part of our complex number. And when we were in junior cert, we wouldn't have been dealing with complex numbers, okay? Our knowledge of the number systems went up to real numbers, and real numbers are made up of irrational and rational numbers. So if you take it right back to your junior cert course, you would have learned about our natural numbers, and then you would have added in your integers, and then we would have added in our rational numbers, and then we would have had our universal set, which was our real numbers, and then out in this section out here, you would have had your irrational numbers. And that would have been our knowledge of our number systems. But then when we got into Leaving Cert, we introduced another number system, which we call complex numbers. And as I've said, complex numbers are made up of our real and our imaginary numbers. And that's where we get a plus bi from. Now, why do we need complex numbers? I suppose there's the next question. Why complicate things? And it basically comes from where mathematicians were trying to solve equations and they couldn't get a real number, so they couldn't find a real solution to the problem. So for example, if we had something x squared is equals to minus 1, but there is no real number squared that gives you an answer of minus 1. So, mathematicians then had a bit of a problem because they said, well, how am I supposed to solve this if there is no real number solutions? So that's where they came up with the idea that x would therefore be equals to plus or minus the square root of minus 1. And it was agreed that the square root of minus 1 would be called I. So mathematicians decided that the square root of minus 1 would be called I, and therefore, instead of it being a real solution, it would be an imaginary solution. So therefore, the solution to this one would have been plus or minus I, which is clearly in the imaginary part of our complex number. Similarly, if we had something like x squared is equals to minus 2, for example, that would then become x is equals to plus or minus the square root of minus 2. And we now know that mathematicians have said that the square root of minus 1 is I. So we would then go and factorize or split up your square root into two separate parts. So take the square root of 2 and then multiply it by the square root of minus 1. So therefore x would be equals to plus or minus root 2, and then the square root of minus 1 would be changed to I, and again we would have our imaginary solution. So that's a really, really important piece of information to be aware of, and therefore if we know that I is equals to the square root of minus 1, it's also really important to know that I squared is equals to minus 1. And those two pieces of information are going to be really useful as we start looking at some exam questions, both from the ordinary level and the higher level curriculum. So before we get into those exam questions then, if we just have a look at where complex numbers appears on the ordinary level and the higher level course. So over on the left hand side here, this is for both ordinary level and higher level, and then on the right hand side this is taken from the higher level section of the course. So for ordinary level and obviously the higher level, you guys need to know this as well. Complex numbers comes up within the number systems part of the syllabus, and if we just look down here, so you can see where the whole idea of number systems is so important, because complex numbers is just another number system. So the first part here is all the stuff that I spoke about earlier that we should know from junior cycle. So your naturals, your integers, your rationals, and your reals. But if we get into the complex numbers kind of section, then you can see that we're expected in the ordinary level and higher level curriculum to be able to investigate the operations of addition, multiplication, subtraction and division with complex numbers in rectangular form. So for ordinary level students, you need to be able to represent it in the form a plus bi, and then you also need to be able to illustrate complex numbers on an Argand diagram, which we'll talk about now in a second. So you need to be able to represent them using kind of like coordinates, and you also need to be able to interpret the modulus. So again, that's another key word that you need to be familiar with about both ordinary level and higher level, and you need to know that it's the distance from the origin on an Argand diagram, and you also need to be able to calculate the complex conjugate, and that will help us when we are trying to divide complex numbers as well. So if you're an ordinary level student, you need to make sure that you know all of those things. If you're a higher level student, you need to know all of those things and the stuff on the right hand side. So when we're talking about the kind of add-on things, then you need to be able to apply the conjugate root theorem to be able to work out other roots of a polynomial. You need to be able to convert complex numbers between rectangular form, which we spoke about already, and you need to also be able to change that into polar form. And that is then going to help us to use De Moivre's theorem and also to solve equations in the form z to the power of n is equals to a. So, and obviously then that will help us when we're converting things into polar form to use with De Moivre's and to apply De Moivre's theorem. You need to be able to prove De Moivre's theorem using induction. So this proof, I'm not going to go through that today, but that proof you will do whenever you do proof by induction in class. So if you haven't done the proof yet, don't panic, because if you haven't done proof by induction, your teacher wouldn't have done this proof with you, as it wouldn't really make any sense. And then finally, you also need to be able to apply your understanding to complex numbers to find things like the nth roots of unity, and apply it to identities as well from the trigonometry section of the course. So guys, what we're going to do to start off with is we're going to look at an ordinary level Leaving Cert question. This is very much relevant to higher level students as well, just to get you thinking about the concept of complex numbers. And what I would say to ordinary level students is this is a very kind of classic question, and what I would advise you guys to do is have a look through this question with me now. I will then be moving on to more higher level topics, so for ordinary level students you won't need to watch the rest of this once we've finished this full question. But what I would recommend you do is go and have a look at a few more ordinary level Leaving Cert questions. As I said to you already, they come up as question 2 and 3 every year, so I would highly recommend you go and actually try a few more of these, and you'll see that they're all very similar to the one that I'm doing here. So I would definitely recommend that for our ordinary level students. So let's get into this then, because again, for both ordinary level and higher level students, this is a good way of recapping the main pieces of information that we need to know about complex numbers. So as we know, complex numbers, when they're written in this form, we say that they are written in rectangular form, and that is in the form a plus bi, where we have our real part and our imaginary part. And in an exam question, you're generally always going to be told a little reminder that I squared is equals to -1, and we can use that to help us in other questions. Generally on the ordinary level course, what you're probably going to be asked to do is maybe add or subtract some of the complex numbers to start off with, and you'll probably be asked to represent them on the Argand diagram as well. So let's just start off with that first of all. So what is an Argand diagram? Well, an Argand diagram is a representation of our complex numbers where we have our real numbers along the x-axis and our imaginary numbers along the y-axis. So that's how we split up our complex number into our reals and our imaginaries. So for our first point here, the point for the number I should say, -2 plus 3i, we want to represent that now on our Argand diagram. So we look at the fact that -2 is our real part, so we're going to go across to -2, and then plus 3i, you don't need to worry about the I, you just look at the number in front of it. So b is 3, positive 3, which is our imaginary part, so we're going to go up here to 3, and that is going to be our first coordinate. So I'm going to label it -2 across and 3 up. This is our point Z1. We're being asked to plot Z2 as well. So I need to go again along my real axis to begin with. We go across to -3, and then this time B is -2. So we're going to go -2 down, and that is where our second coordinate is going to be, and that is the point Z2. So now we want to go and plot Z3, because we're being asked to plot Z1, Z2 and Z3 on the Argand diagram and label each point clearly. But we're going to need to go and do a little bit of work now for Z3, because as we can see, Z3 we're being told is Z1 minus Z2. So I'm going to write this out now. So it's going to be -2 plus 3i minus. Now make sure you put Z2 into a bracket, because that minus needs to hit off everything inside here, not just the -3. So that's going to give me -2 plus 3i plus 3 plus 2i. Now we're going to go and add it together. So this is a good recap then for all of us on adding and subtracting complex numbers. So you always take the reals and put them together, and then the imaginaries go together. So it's going to be minus 2 plus 3, which is going to give me 1, and then plus 3i plus 2i, which is going to give me plus 5i. So now I have Z3, but let's not forget we need to label each point on our Argand diagram. So that means I'm going to have to go 1 across and 5 up. So that's going to be located here. And I'm going to make sure I label that Z3. So that's the first part of that question done. And on this particular exam question on the ordinary level course, that first part A was worth 15 marks. So you can see you're getting 15 out of 25 for simply applying a little bit of adding and subtracting rules and also labeling them on the Argand diagram. Okay, the next thing then is a really good recap then of the whole idea of our modulus, which again you need to know for both the higher level and the ordinary level leaving cert. So when we see the lines on either side of our complex number, it means that we're being asked to work out the modulus. And the modulus is the distance between your complex number and the origin. And the origin is the point 0, 0. So for example, if we're being asked to work out the modulus of Z3, we're being asked to work out the distance between Z3 and 0, 0. Now, sorry, forgive me, that's not a very straight line, but you get the idea. That's the straight line distance using a ruler down to the point 0, 0. So they're asking us to investigate if that distance is the same as the distance from Z1 to the origin plus the distance of Z2 to the origin. So the way that we're going to work out the modulus is we're going to apply Pythagoras' theorem. Now, what you will notice is you can kind of apply Pythagoras' theorem nearly in disguise here. So a lot of you might remember when you did the modulus in class that you learned this. So it's the square root of a squared plus b squared. Now that is literally just Pythagoras' theorem, because if you think about it, and again my line is not straight there at all, but if you think about it, this is just a right angle triangle. So if we're being asked to work out this distance here, we're taking the distance here, which is your imaginary, and your distance here, which is your real distance. You're squaring them, you're adding them together, and then you're square rooting them. And that is Pythagoras' theorem. But as I said to you, that's the formula that you may be familiar with from class. So let's go and work out the modulus of Z3 to begin with. So the modulus of Z3 is going to be equals to the square root of a squared plus b squared. So again, this is my Z3 up here. So it's going to be 1 squared plus 5 squared. Now remember, it's not bi squared, it's just b squared, so you don't put the I in there at all. So that is going to give me the square root of 26. So I'm going to leave that there for a second, and then I'm going to go and work out my modulus of Z1, and I'll work out my modulus of Z2. So my modulus of Z1 is going to be equals to the square root of minus 2 squared plus 3 squared. And that is going to give me the square root of 4 plus 9, which gives me 13. So I'll leave that there for a second. And I'm also going to work out my modulus of Z2. And Z2 is up there. So that is going to give me the square root of minus 3 squared plus minus 2 squared. So that's going to give me 9 plus 4 again. So that's going to give me the square root of 13. So they're asking us to investigate if the modulus of Z3 is equal to the modulus of Z1 plus the modulus of Z2. So let's go and fill that in then. So the modulus of Z3 we said is root 26, and they're asking us, is that equals to the square root of 13 plus the square root of 13? Now on kind of first glance, we may fall into the trap of thinking, oh yeah, sure, 13 plus 13 gives me 26, but the square root of 26 is not equals to 2 root 13, okay? When they're in the square roots, you don't obviously just add them together because that wouldn't make any sense. So you could add root 13 and root 13 together, but that just gives us 2 root 13, and that would give you an answer in and around kind of like 7, whereas the square root of 26, if we worked out that would give you an answer of around 5. So we can clearly see that they are not equals to each other. So you can see why I've written my equal sign with the line in between it, and you could also write down a little sentence there. Therefore, and rewrite out your your investigation question. Therefore, the modulus of Z3 is not equals to, so you can put your line through it, the modulus of Z1 plus the modulus of Z2. So moving on to part C of this question then from the ordinary level Leaving Cert, this is a really good recap for all of us, both higher level and ordinary level students, on the whole idea of our dividing complex numbers and also using our knowledge of a complex conjugate. So this would normally be on the same page as your other questions in your Leaving Cert, but what I'll do here, just because we don't have it in front of us, is I'm going to just write down what Z1 and Z2 are. So Z1 we were told is minus 2 plus 3i, and Z2 is equals to minus 3 minus 2i. And we can see here we're being asked to write Z4 in the form x plus yi. So therefore we're being asked to write it in rectangular form. So to start off with, let's just rewrite it out with the complex numbers written in for Z1 and Z2. So that's minus 2 plus 3i over minus 3 minus 2i. So at this stage in your question then we're thinking, okay, I need to rewrite this in rectangular form, and therefore there shouldn't be a fraction. So we need to get rid of the fraction here. We need to get rid of the denominator. And what you would have learned in the complex numbers chapter is that whenever we want to get rid of the complex numbers in our denominator, that we need to use the whole idea of a conjugate. And in particular, a complex conjugate. So for example, if a plus bi is a complex number, well then a minus bi would be considered its complex conjugate, because what will happen is when we multiply those two complex numbers by each other, it will cancel out the imaginaries, or the imaginaries are going to go to 0 because one is a plus and one is a minus, and therefore when we add them together it's going to give me 0. So our trick that we need to know with complex numbers is if we are ever asked to get rid of a fraction, i.e. divide in a complex number, we need to multiply the denominator by its complex conjugate. So you need to look at the denominator and you need to say to yourself, what is the conjugate of minus 3 minus 2i? And use this to help you. So the real number stays as it is, but the imaginary number changes sign. So that's going to become plus 2i. Now, this is an expression, and we can't just magically multiply one part of the fraction by something else, because that's going to change the whole value of that expression. So what we need to do then is we need to also multiply the top of the fraction by the complex conjugate, because that will mean that we're actually just multiplying the whole thing by 1, because anything divided by itself gives you 1. So we're not actually going to change the value of the expression. So that is the trick that we need to know. When we're dividing complex numbers, we always multiply the top and the bottom by the conjugate of the denominator, which is the bottom of your fraction. So now we need to go and apply our multiplication rules for complex numbers, which are very straightforward, okay? So you can nearly imagine these are all in brackets, and we just have the top multiplied by the top, because that is our rule for fractions as well. When you're multiplying fractions by each other, you do the top multiplied by the top and the bottom multiplied by the bottom. So we're going to do the minus 2 multiplied by minus 3 and then by 2i, and then 3i by minus 3 and 3i by 2i. So all together then, let's have a look at that. So minus 2 by minus 3 is going to give me 6. Minus 2 by plus 2i is going to give me minus 4i. Then 3i multiplied by minus 3 is going to give me minus 9i. And we need to be careful for this one. So this is going to be plus 3i multiplied by plus 2i. So that is going to give me plus 6i squared. And I'm going to come back to that in a minute, okay? But we are going to have to change that because we know what I squared is equals to. So I'm just going to come back to that one in a second. And we'll multiply the bottom by each other. So minus 3 by minus 3 gives me 9. Minus 3 by plus 2i gives me minus 6i. Minus 2i multiplied by minus 3 gives me plus 6i. And then finally, minus 2i by plus 2i gives me minus 4i squared again. And we need to be careful with that. So what we need to remember is earlier on in today's video, I reminded you that I squared is equals to minus 1. And we were also told that at the start of the question. So again, I know I don't have it here because I've just zoomed in on part C, but up the top of that exam question, you do actually have that written down. So therefore, we're not going to leave them as I squared. We're going to substitute minus 1 in its place. So we'll do that now, and I'm also going to tidy up my imaginary numbers while I'm at it. So on the top of my fraction then, I'm going to have 6, and then I've got minus 4i minus 9i. So that's going to give me minus 13i. And then it's going to be plus 6, and I'm going to take away the I squared, and I'm going to put my minus 1 in there instead. Similarly then, on the bottom of my fraction, I'm going to tidy up the imaginaries. But what we notice is I have minus 6i and plus 6i. And when you add them together, that's going to give you 0. And that's exactly what we were hoping to happen. And I'm going to then write down my 9 minus 4, and I'm going to take away the I squared and put minus 1 in its place. So therefore, on the top of my fraction, I have 6 minus 13i, and plus 6 by minus 1 gives me minus 6. So 6 minus 6 is going to go to 0. So I'm only going to be left with an imaginary part here, which is minus 13i. And then on the bottom of my fraction, I'm going to have 9, and minus 4 by minus 1 gives me plus 4. So that is going to give me plus 13. And that can therefore simplify into, the 13 will go into the minus 13 minus 1 times. So we're going to be left with minus I. And if you remember, we're being asked to write this in the form x plus yi. So I'm going to finish this off as 0 plus, or sorry, it's going to be minus, isn't it? So it's going to be 0 minus 1i there as my final answer, because we're being asked to write it in the form x plus yi, where x and y are elements of OR. Now, I wouldn't always normally write the 1 in there, because we know normally we wouldn't, but just because it was asked in this specific way, to be safe, I'm going to write it as 0 minus 1i. And that question was worth 5 marks on the Ordinary Level Leaving Cert. So for any Ordinary Level students watching today, we're going to leave it there for the Ordinary Level content. We've gone through everything that you guys are expected to know. And as I said, what I would recommend for you guys to do now is to go and have a look at a few more of the exam questions from the Leaving Cert. And there's also a discount code, which I'm going to talk to you about as well. Just I'm conscious that you guys won't be watching the rest of the video. So if anyone is interested in seeing more of my style of teaching with the maths course, we have the entire Leaving Cert higher level and Ordinary Level course done in video tutorials, notes, PowerPoints, etc. So if anyone would like to go on to ExamRevision.ie and you're interested in buying a subscription, we are running 20% off until Sunday night at just before midnight, and the code that you need to know is complex 20. So if you would like to take out a subscription, it would be a great idea to do it this weekend, as it will give you, Complex 20 will give you 20% off. For our higher level students, if you guys want to stay watching the video, and I'm going to take you guys through some of the main higher level topics for the rest of today's Saturday session. So the next thing I want to talk to you about then in the higher level course is the conjugate root theorem. So we already spoke about the whole idea that if z is a complex number in the form a plus bi, well then its complex conjugate would be a minus bi. And what the conjugate root theorem states is that if a polynomial that has real coefficients, so that's really important. So basically, if you have a polynomial that all the coefficients are real numbers, and we know that z is one of the roots of that particular polynomial, well then, without even thinking about it, we know that the conjugate of z is also a root. So let's say in a question where we have a polynomial with real coefficients, and I tell you that z is one of the roots. So let's say z is 2 plus 5i. And if that polynomial has real coefficients, so basically it has real numbers in front of its variables, well then without even thinking about it, I know that z's conjugate, which would be 2 minus 5i, is also going to be a root. And believe it or not, that has come up on the Leaving Cert course before as a part A question, where they say something along the lines of 2 plus 5i is a root of the polynomial blah 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 with real coefficients, write down another root. And there's literally a tiny space for you to write your answer, and that's literally all you would have to write down, 2 minus 5i. And that is based on your conjugate root theorem. So the next thing I want to talk to you about then is polar form. So we mentioned previously that when we have numbers, complex numbers written in the form a plus bi, we call that rectangular form. But higher level students are also expected to be able to convert something in rectangular form into polar form and vice versa. So in order to do that, I need to talk to you about another thing that's linked with our Argand diagram. So far we have spoken about the Argand diagram, and that if we have a complex number, that we can work out the distance between that complex number and the origin at 0, 0, and we call that the modulus. But there's another thing that we also have to work out if we want to go and turn something into polar form. And the other thing that we need to be able to work out is something called the argument. So you've got your modulus, which we've looked at already, but then we also have this thing called the argument. And the argument is the angle theta. So I'll just label it in here. So it's this angle here. So it's the angle between the line segment joining a complex number to the origin. So that's the black line that I've just drawn there, which would be our modulus, and the positive x-axis. So basically the angle between the positive x-axis and the line joining your complex number to the origin is called the argument. And the angle theta is anti-clockwise. And you need to be able to work out that argument if you want to go and convert something into polar form. So the two things that we're going to need to know for polar form is the modulus and the argument. But just remember that the argument is always the angle between the line joining your complex number to the origin and the positive x-axis. So we'll have to look at a few different examples of that now in a second of the easiest way to calculate it. So if we start off with then looking at an example where we're being asked to write a complex number which is currently in rectangular form, and we're being asked to change it into polar form. So as I said already, the two things you need to remember then when you want to write something in polar form is you need the modulus, which we use the letter or to represent, and we also need to know the argument, which is theta. So what I would suggest you do as your first step whenever you want to write something in polar form is you draw it as a quick sketch for yourself to kind of imagine which quadrant it's in. So minus root 3 plus I. So I know I'm going to be over here on the left hand side in the negative sense of my real numbers, and then I'm going to be up here in the positive sense of my imaginaries. So roughly speaking, that is where our imaginary or our complex number is going to be located. Now, I have two things I need to work out then. I need to work out my modulus, which I've drawn in already there, and I also need to work out my argument. But importantly, we learned that the argument is always the positive sense of the x-axis anti-clockwise around to that line. So therefore, this is where my angle is going to be located. Okay, and that's an important thing for us in a minute. So let's kind of mark in what we know then. So if I turn this into a little right angle triangle here, we know that the distance from the origin to our point is root 3. Note that I haven't written in minus root 3 there because it's a positive distance, and the distance from my x-axis up to my point is going to be 1. So when we're labeling the distances, you could, if you wanted to, if you felt more comfortable, you could redraw it out so you're not kind of thinking about it on the Argand diagram. But I'm not writing in minus root 3 there because root 3 in this particular format, we're thinking of it as a distance. Okay, so the first thing we're going to do then is we need to work out our modulus. So step 2 of this then is let's work out the modulus. And we know the modulus is the square root of a squared plus b squared, which, as I've mentioned previously, is just Pythagoras' theorem. So it's going to be the square root of 1 squared and sorry, if I'm keeping it as a, I should really be doing it the other way around. So it's going to be the square root of minus root 3 squared plus b, which is just the number in front of the I, which is going to be 1. So that is going to give me the square root of 4, which is going to simplify to 2. So therefore, or is equals to 2. So I now know first part of polar form I have done. I know my modulus is equals to 2. So the next thing I need to work out then is my argument. So step 3 in this is we need to go and work out your argument. And we know the argument is located here on my argand diagram. But annoyingly enough, the information that I have in this right angle triangle does not include the argument. So what we're going to do is we're going to go and work out this angle here. Because if I work out this angle here, I know that altogether that line is going to add up to 180 degrees, or pi. So therefore, if I can work out what alpha is, I can subtract it away and it will give me my argument. So that's what we're going to do here. So as I mentioned before, I always like to kind of redraw it as its own little right angle triangle. And we're going to think about the fact, as you know, and you don't even need to learn off any new formulae for this. This is a right angle triangle, and we can clearly see here that's H, that's O, and that's A. So we're going to be dealing with O and A, which is tan. So as always, we're going to write down then tan of alpha is equals to O over A. So it's going to be 1 over root 3. And then we're going to go and figure out what our angle is equals to. So on our calculators then, we're going to do tan inverse of 1 over root 3. And that is going to give me, I'm going to keep this in radians, because generally speaking that's what we would use in a complex number question, but again it will depend when you're looking at it yourselves. So into your calculator you're going to do tan inverse 1 over the square root of 3. That's going to give you 30 degrees, but if you then go and divide that by 180 and multiply it by pi, you're going to get pi over 6. Now, very important not to fall into the trap of thinking that we have worked out the argument. We have not. We've worked out what alpha is, but we now need to go and subtract pi, or subtract it from pi to get what theta is going to be equals to. So theta is going to be equals to pi minus pi over 6, which gives me 5 pi over 6. Remember, that is the exact same as saying 180 minus the 30, which would obviously give you 150 degrees, which is 5 pi over 6 radians. So we now have our two things. We have our modulus, which is 2, and we have our theta, which is 5 pi over 6. So I'm now ready to go and write this in polar form. So to write a complex number in polar form, what we need to remember is we need to, sorry, let me just write this down here. What we need to remember is the following formula. Okay, so if you're ever asked to write something in polar form, you need to remember it's or bracket cos theta plus I sine theta. Okay, so that is your complex number in polar form. So therefore, or we already have worked out as 2, remember that's our modulus, bracket cos theta, which we now know is 5 pi over 6, plus I sine theta, which is also 5 pi over 6. And that is your final answer. That is your rectangular number minus root 3 plus I written in polar form, and that is your final answer. Now, building on from that then, we have something called De Moivre's theorem. So De Moivre's theorem looks very similar, I suppose, to what we were looking at just now when we were talking about polar form. So the first thing to know with De Moivre's theorem is that the complex number needs to be written in polar form in order to apply it. And basically what De Moivre's theorem states, it is on page 20 of your formula tables, is that if we have a complex number and we raise it to the power of n, that we can apply that then to a complex number in polar form by raising the modulus to the power of n, but by multiplying the argument by n rather than raising it to the power of n. So it will make more sense now in a second when we have a look at a question, but it's just to remind you that De Moivre's theorem, you need to have the complex number written in polar form, and to apply it, you raise the modulus as you would expect to the power of n, but you multiply the arguments or the angles by the number rather than raising them to that power as well. So now we're going to look at a higher level leaving cert question, and this is going to apply all the bits and pieces that we've been speaking about together from the last few slides. So the first part of this question says that minus 4 plus 3i is one root of the equation az squared plus bz plus c equals to 0, where a, b and c are elements of OR. That's really important because that's them telling us that a, b and c are real numbers, and I squared is equals to minus 1. Write the other root. So this is where you need to jump in and say, oh yeah, perfect, we have all real coefficients. I know one of the roots is a complex number, therefore based on my conjugate root theorem, the other root must be the conjugate of minus 4 plus 3i, which is going to be minus 4 minus 3i. And it's as simple as that. You're done and dusted for part A of this question, and that was worth 5 marks in this particular exam question. The next part then is asking us to use de Moivre's theorem to express 1 plus I raised to the 8 in its simplest form. So this is a classic de Moivre's theorem question where we are raising a complex number to a particular power. But what we need to remember straight away is before we can go and apply de Moivre's theorem, we have to rewrite the complex number, which is currently in rectangular form, into polar form. So let's go and do that straight away. So this is exactly like what we looked at in the last example. So our first step is we're going to go and rewrite this as on an arrogant diagram. So it's going to be 1 across and 1 up. So it's going to look something like this. And we know that it was 1 across, so that's going to be 1 along our real axis, and then it was 1 up. So if I wanted to redraw this then as a little right angle triangle, we can see that it would be 1 along here and 1 along here. And we know that in order to write things in polar form, we need to work out OR, which is our modulus, and theta, which is our argument. And luckily enough for us in this one, theta is actually going to be in our right angle triangle straight away because we're not going into any of the other quadrants. So let's start off then by working out the modulus, and we know that the modulus OR is equals to the square root of a squared plus b squared, so it's going to be 1 squared plus 1 squared. So OR is equals to root 2. Now let's go and work out the argument. So we know we're going to be dealing with tan again because we can see here in a right angle triangle we've got the opposite and the adjacent. So it's going to be tan theta is equals to 1 over 1. Take note of the fact that I'm jumping straight in to say tan theta in this one rather than tan alpha because it is the theta angle that I'm looking for. So on our calculators, we're going to go and do tan inverse of 1. Again, I'm going to write this in radians. So it's 45 degrees. So I'm going to do 45 degrees divided by 180 multiplied by pi. So it's going to be pi over 4. So that is my argument as my angle. Now I'm going to go and apply all that together, and I know when I want to write something in polar form, it's OR bracket cos theta plus I sine theta. So that is going to give me OR, which is my modulus, which is root 2, bracket cos pi over 4 plus I sine pi over 4. Now, I suppose the mistake I'd be afraid that you might run into is that you've done all that hard work and you might forget that we haven't actually answered the question yet. We've just done the first part, which is I need to rewrite this in polar form. So I've done that bit now. So now I need to go on to, I suppose, step 2 of this question, which is I need to apply de Moivre's theorem. So de Moivre's theorem is asking me to take my complex number in rectangular form and raise it to the power of 8. So what I need to now go and do is say, well, 1 plus I raised to the 8 is the same as, so I'm going to take my number in polar form and I have to go and raise that to the power of 8. So therefore I have to apply de Moivre's theorem. So again, I can go to my formula tables if I need a recap of this. And what happens with de Moivre's theorem is that the 8 is going to come and sit on the modulus's shoulder as you would expect, but instead of it raising the arguments to the power of 8, it's going to multiply the arguments by 8. So that's going to give me 8 pi over 4. Obviously that does simplify, but I'm just keeping it in that format first. and we're being asked to express this in its simplest form. So I'm going to go and rewrite this in rectangular form now in a second. So root 2 raised to the power of 8 is going to give me 16. And then on my calculator, make sure it's in radians if you're going to leave in your pi, or you can obviously change it to degrees if you would like. So that is going to give me cos 8 pi over 4, which is the same as just 2 pi, is going to give me 1. So it's going to be 1 plus, and then I'm going to do the same for sine. So again, put it into radians if you want to keep your pi in there. So when I pop that into my calculator, then it is going to give me, so it's going to go in there twice, so it's going to give me an answer of 0. So that's going to be plus 0i. So therefore, when I go and multiply that out, I'm going to be left with a simple answer of just 16. You can write it as plus 0i if you want, but in this particular case, we're just being asked to write it in its simplest form. So 16 is our final answer, and that is De Moivre's theorem done out there for you, where we have converted it into polar form, and then we've applied De Moivre's theorem and written our answer in its simplest form. So the next example I want to show you is, I suppose, where I don't want people falling into the trap of thinking that they can use the conjugate root theorem. So in this particular example, you can see that we're told that 1 plus I is a root of the equation. Z squared plus minus 2 plus IZ plus 3 minus I equals to 0. Find the other root. Now, the trap that you would fall into is you would think, okay, Gran, I can just write down 1 minus I, but this is why it's so important that you read your questions properly, because in order to use the conjugate root theorem, remember we said that the coefficients have to be real numbers, but we can clearly see here that the number in front of Z is a complex number and it's not a real number. So therefore we can't use the conjugate root theorem. So we need to come up with another strategy. Now, there's loads of ways of answering this, but personally, I like to bring it back to your algebra chapter, and I like to think, well, okay, we're being told that this is a root of the equation, and we're being asked to work out another root. And if we use the whole idea of roots and factors, and if we say, okay, well, if this is a root, I can write it as Z equals 1 plus I, well, therefore, I can bring everything over to the other side of my equal sign, and therefore, this is a factor. So how I like to teach this one is I say, okay, well, if this is a factor, and I know that a factor divides in evenly into my cubic, or my quadratic, I should say, pardon me, therefore, if I divide that into my quadratic, it should give me my other factor. So that's exactly what I'm going to do. So I'm going to divide Z minus 1 minus I into this quadratic. I'm going to just multiply out the Z bracket there. So that's going to be minus 2Z plus IZ plus 3 minus 1. And I'm going to do long division. So what you multiply Z by to get Z squared, it's going to be Z. I'm going to pop that up here, and then I'm going to multiply it by everything on the outside. So that's going to give me Z squared minus Z minus IZ. I'm going to come along now and change all the signs. So that becomes a minus, that becomes a plus, and that becomes a plus. And I'm going to do my column addition. So they're going to go to 0. That's going to give me minus 2Z plus Z. So that's going to give me minus Z. And then plus IZ is going to give me plus 2IZ. And I'm going to bring down my that entire number there, because remember that's kind of just your constant. So that's going to be 3 minus I. And I'm going to start the whole process again. So what do I multiply Z by to get minus Z? It's going to be minus 1. So let's go and multiply that out then. So that's going to give me minus Z plus 1 plus I. And let's go and change all the signs. That's going to be a plus, that's going to be a minus, and that's going to be a minus. At this stage, don't panic that everything doesn't completely cancel out just yet. So what I'm noticing here is I don't have anything else down here to add on to my Z. So I'm just going to leave that. Remember, we're just adding all this stuff together. So it's going to be 2IZ. And then I've got my 3 minus 1, so that's going to give me plus 2. And I've got my minus I, so that's going to give me minus 2i. So I'm going to have to go and do this one more time. So what do I multiply z by to get 2iz? Well, it's going to be plus 2i. And I'm going to go and multiply it by everything again. So it's going to be 2iz minus 2i minus 2i squared. But again, remember, I need to be really careful with this because I know that's actually going to give me minus 2 by minus 1, which is going to give me 2. So that's actually going to be positive 2. So I'll rewrite this all out because I'm just going to need to be really careful with my signs now, because then I need to remember that I go and change all the signs. That's going to be a minus, that's going to be a plus, and that's going to then change to a minus. And hopefully if I've done this properly, they should all cancel, so, or go to 0. So 2i minus 2i minus 2i plus 2i and plus 2 minus 2. We're left with 0. So that shows me that this is the other factor. So z minus 1 plus 2i is a factor, but remember they want the other root, so I need to bring it over to the other side of my equal sign. So z is going to be equals to 1 minus 2i, and that is your other root in this question. So that's just to show you why it's really important that you check to make sure if you're going to use your conjugate root theorem, the coefficients have to be real numbers. In this question they weren't, so you're going to have to use another strategy to find the other root. Okay, so the next thing I want to talk to you about then that is on the Leaving Cert higher level course is the whole idea of roots of complex numbers. And we're going to be using de Moivre's theorem again to help us find the roots of an equation. So why do we need this? Okay, so if we start off with z to the power of n is equals to a plus bi. And this is an equation, okay? And let's say in the question we're trying to figure out what z is equals to. Well, therefore, I need to get rid of the power of n. And we know in any kind of basic question, if I said to you x cubed is equals to 27, and I asked you to get what x is, you would be able to cube root both sides to get your answer. And we're going to have to do the exact same thing here, even though this is a complex number. So in order for me to get rid of the power of z, I need to root to that power of z of each side, which remember is the same as writing it as 1 to the power of n. So just like I did in my example there on the right hand side, we would need to find the nth root of both sides. That would leave me with z on the left, and on the right hand side, instead of writing it as the nth root, we could change that to a plus bi raised to the 1 over n. And this is where the whole idea of roots of a complex number comes into play. Now, in order for us to work this out, we can go and then apply de Moivre's theorem, because we already know that if we raise anything to a power, that de Moivre's theorem is going to come in and help us. But in order to do that, because there's a chance that we're going to have more than one answer here, instead of just writing the number in polar form, we need to write it in a thing called general polar form, because that will allow for us to work out more than one answer as we're going around our Argand diagram. So to write something in general polar form, it's the exact same as polar form, except we're just going to add one extra thing in. So it's going to be or bracket cos, so or bracket cos, and then we're going to have theta plus 2n pi, so to give it that cyclical nature, plus I sine, and the exact same thing, theta plus 2n pi. And that is how we write our complex numbers in general polar form, and that's going to be really helpful then for the next exam question that we're going to have a look at. So the first part of this exam question, again, it's a higher level Leaving Cert question, is just asking you to write this complex number that's currently in rectangular form into polar form. So nothing difficult here. We've gone through one of these questions already, but we'll have a quick run through it now nice and quickly. So step 1, if we want to write anything in polar form, we need to remember to draw ourselves a little diagram. So it's going to be 2 across and minus 2 root 3 down. So we're going to be down in this section of our Argand diagram, and again I'm going to mark in my modulus and I'm going to mark in my argument. So remember, the argument is always anti-clockwise from the positive sense of the x-axis all the way around. So this is our argument. now I'm going to go and just draw a little sketch then of this right angle triangle for myself and fill in what we know. So we know that this is 2 across and it is 2 root 3 down, but remember I'm going to keep it as positive. And I know in this particular right angle triangle that theta is not there, like theta is out here, it's not in here, but I can work this angle out. So what we're going to do is we're going to go and work this angle out again, which I'm going to call alpha, and then we can use that and subtract it from 360 degrees or 2 pi to go and work out what theta is. So let's go and work out our modulus and our argument. So our modulus is going to be equals to the square root of 2 squared plus 2 root 3 squared, and that is going to give me a modulus of 4. And now I'm going to go and work out my argument, okay? So in order to do that, I have to actually start off by working out theta. So, start by working out alpha, I should say. So as always, I have my opposite and my adjacent, so I'm going to be using tan. So tan alpha is equals to O over A. So alpha is going to be equals to, and I think that's going to give me 60 degrees. Let me just double check here now. So it's 2 root 3 all over 2. Yeah, so that's 60 degrees. I'm going to change it into radians here, and it's important for this one because they're actually explicitly telling me it should be in radians. So that is going to give me pi over 3. But now I need to go and work out what my theta is. So theta is going to be equals to 360 degrees, which is 2 pi minus pi over 3. So that's going to give me theta is equals to 5 pi over 3. And then finally, bringing that all together, then we need to write this in our polar form. So it's going to be V is equals to 4 bracket cos 5 pi over 3 plus I sine 5 pi over 3. And that is your final answer for the first part of this question. And now we're going to have a look at part 2, which is where we're going to be working out the roots of complex equations. So in this question, or this follow-up part then, we're being asked to use your answer to part BI to find 2 possible values of W where W squared is equals to V. So really importantly to start off with, they're asking us to work out 2 values of W. So don't overcomplicate it. Look at this little equation to start off with and think, okay, that means I need to get rid of the squared up on the W's shoulder. So I need to square root both sides. Okay, so I need to square root both sides, which is the same then as saying V raised to the power of a half. Okay, so that's what I'm basically trying to work out. If I can work out what V is raised to the power of a half, well then I've gone and worked out what W is, which is exactly what we're being asked to do in the question. But we know from the previous part that we have worked out what V is. And we were given V in its simplest form, in rectangular form. We were told that V was equals to 2 minus 2 root 3i. However, that's not going to help us because I need to raise this complex number to a power. And I know in order to do that, I need it to be in, I need to use de Moivre's theorem. And in order for me to use de Moivre's theorem, I need it to be written in rectangular form. So this format is not going to work. I need to use my rectangular form, my polar form, which I've just done in the previous question. So I don't need to go and actually work that all out again. But I'm going to actually write it in general polar form because there's going to be more than one answer here. So I'm going to go back to my previous question then, and I'm going to rewrite V in polar form. But as I said, it's not just polar form. I'm going to add in my 2n pi in here as well, because that's how I write it as general polar form. So therefore, I'm going to write down then that W is equals to bracket. So it's going to be 4 bracket cos, and it's 5 pi over 3, and that's what I had already, but I'm going to add in plus 2n pi plus I sine bracket 5 pi over 3 plus 2n pi. So the only thing I've done so far is I've written it in polar form, but I've also added in my general polar form. And I'm raising it all to the power of a half, which is what we've worked out we need to do in order to find our value of W. So now I'm going to go and apply de Moivre's theorem. And de Moivre's theorem states that I take whatever I'm raising my bracket to and I multiply it, I bring it down and put it on the modulus's shoulder. So that's going to become 4 to the power of a half. And then I'm going to come in here and I'm going to apply it to my argument. But remember, I don't raise them to the power of a half, I multiply them all by a half. So my first fraction here, then I have to multiply that by a half. So that's going to become 5 pi by 1 just gives me 1, and then 3 by 2 gives me 6. And similarly, I'm going to multiply this by a half as well. So that's going to become 2n pi all over 2. And then I'll do the same thing here. So that's going to become 5 pi over 6 plus 2n pi all over 2. Now, 4 to the raised to the half, that's the same as the square root of 4, which is going to give me 2. And before I go and do anything else, I'm just going to simplify this a little bit. So that's going to stay as this, but then those 2's are going to go to 1. So that's going to leave me with n pi plus I sine. You don't have to do the simplifying, but it's just to show you, plus n pi. Okay, now at this stage you're thinking, hang on, there should be 2 answers, and right now there's an unknown there, n. What am I supposed to do? So what you will always do in these questions is you need to substitute in, and we're going to start always with 0. So I'm going to start by subbing in n equals to 0. And because there's only 2 solutions, it will mean I'll sub in n equals to 0, and I'm also going to sub in n equals to 1. Now let's say I had raised that to the power of 3. There would have been 3 solutions, so I'd sub in 0, 1 and 2. But you always start off with 0 and then add 1 on each time. So if I sub in 0, basically there's just going to be a 0 here and a 0 here. So that bit's going to go. So I'm going to be left with 2 bracket, and then it's just going to be cos 5 pi over 6 plus I sine 5 pi over 6. Now, we need to give our answers in the form A plus IB or BI. So I need to actually go and use my calculator to figure out what cos 5 pi over 6 is going to be. Now, if you leave it as radians, or if you leave the pi in there, you're going to have to convert your calculator into radians, so make sure or is up the top, or you could just put 180 in there, multiply by 180 and get rid of the pi if you wanted to. So when I pop that into my calculator, so I'm just putting cos 5 pi over 6, when my calculator is in radians, I'm getting minus root 3 over 2, plus, and then I'm going to go and put sine 5 pi over 6 into my calculator, and that is giving me a half. Now remember that I is there, so it's going to be a half I, and therefore I can multiply the 2 on the outside, so that's going to give me minus the square root of 3 plus I. So that is my first answer, but remember there should be 2 solutions, so I need to go and sub 1 in now. So therefore that's going to give me 2 bracket cos 5 pi over 6 plus pi, because it's just one of them, plus I sine 5 pi over 6 plus pi. And again, we're going to need to do a little bit of work here now on our calculators. So you could simplify them if you wanted to. So if you did 5 pi over 6 plus pi, that's going to give us 11 pi over 6. Now, do you have to do that? Absolutely not. You could just pop it into your calculator as cos bracket 5 pi over 6 plus pi. That would work as well. It's really just personal preference if you want to tidy them up or not. So now let's go and pop that into our calculators. So I'm going to put in cos, and again, make sure your calculator is in radians. So that's going to be 11 pi over 6. And I'm getting an answer of root 3 over 2. And then I'm going to do the same for sine, and it's going to be 11 pi over 6. And that is giving me minus a half. And again, make sure I'm popping the I on there. And then I'm going to multiply that out. So I'm just running out of space here. So 2 multiplied by root 3 over 2, that's going to give me root 3. And it's going to be minus I. So my second solution is root 3 minus I. So again, if in these questions you're ever in doubt, keep it simple. Think about what value you're trying to get the solutions for. Get rid of the power, whether it's squared, cubed, power of 4. Use de Moivre's theorem. but make sure your answer is in general polar form before you apply De Moivre's theorem, and then go and sub in 0, 1, 2, and whatever you might need to up until you have the amount of solutions that you should have for your question. Now, I'm not going to have time to go through this in detail, but I just wanted to mention while we were on the whole idea of roots of complex numbers, just to say that if you are specifically asked to find, for example, the cubed roots of unity, this is something that is specifically highlighted in the syllabus. So if you're asked to work out, let's say, the cubed roots of unity, that means you're being asked to solve the equation z cubed equals to 1. Okay, so for unity, it means it's equals to 1. So therefore, that's the same as 1 plus 0i. So just in the off chance you were asked to solve this, that's obviously the first thing you need to know how to set this question up. So the cubed root of unity would be z to the power of 3 is equals to 1 plus 0i. And if you're asked to solve this or to find them, that means you're trying to get z by itself. So like I spoke to you about already, that means that you're trying to find the cubed root of both sides, which would be the same as 1 plus 0i raised to the power of a third. And therefore we're right back into the same question as I showed you on the last slide, where you're having to go and write this as general polar form. Then you go and you apply De Moivre's theorem, and then you go and sub in 0, 1 and 2, because this time, because it's cubed, there's 3 solutions, and then you get your answer that way. So it's just in case something like that came up, just to show you how that works. And just the very last thing I want to show you in today's video before we finish up is just a question where you're being asked to rewrite a kind of a weird looking complex number in the form a plus bi, because I do find that this type of question can really, I suppose, catch you out because you're not really sure how to start it. So if you're ever being given a complex number which looks a little bit confusing and you're being asked to write it in the form a plus bi, the easiest way of doing this is equating the reals with the reals and the imaginaries with the imaginaries. So what I would recommend is that you start off by letting a plus bi equals to the square root of whatever you're being given. So in this case, it's the square root of -1 minus root 3i. And basically, we're going to equate them. So we're going to say, well, yes, I know that this is a complex number, so it can be written in this form. So I need to go and try and figure out how to do that. So the first thing you're going to do, you've got a little equation here, is we want to get rid of the square root. So I'm going to square both sides. And on the left-hand side, then, we're going to have to multiply it out. So it's going to be a squared plus 2, I'm going to just do this quickly, plus 2abi minus b squared. And then we're going to go and square out the right-hand side as well. So that's going to mean that the square root and the square root are going to be inverses of each other, so they'll cancel, and I'm going to be left with -1 minus root 3i. So at this stage in the question then, what we want to do is we want to equate the reals with the reals and the imaginaries with the imaginaries. So you might want to rewrite this out. So the reals would be this part and this part, so that's going to be a squared minus b squared, and then the imaginary is obviously the 2abi, and again that's equals to this. So what we're going to do now is we're going to equate the real numbers to each other. So that means that a squared minus b squared is going to be equals to -1. So a squared minus b squared is equals to -1. And then we're going to equate the imaginaries. So that's going to be 2ab is equals to, and just be careful with your signs, it's going to be minus root 3. Now at this stage then we just have to go and solve these simultaneously, because we can see here very clearly that we've got two unknowns with two equations. And what I would probably recommend is you go to the imaginary one, so the 2ab is equals to minus root 3, get one of the letters by itself. So let's say we get the a by itself, so that's going to give you a is equals to minus root 3 all over 2b, and then you'll go and you'll sub that in over here. You'll substitute it in. I'm not going to go and do all that out now, but you'll go and substitute that in, and you'll end up with b squared is equals to root 3 over 2. So therefore b is going to be equals to plus or minus the square root of 3 over 2. The other solution that you end up getting, just so that for when you go and if you wanted to go and do this out yourself, is you would have gotten b squared is equals to that, but you also would have gotten 2b squared is equals to minus 1. But that actually, there is no solution because you're not going to be able to find the square root of a negative, so that one won't work. So then that's going to be your answer for B. Then you're going to go and sub both of those in then to your A, and you're going to end up with that A is equals to plus or minus 1 over root 2, or plus or minus root 2 over 2. And they are your answers. So that means you're going to have a few different versions then of your answers, and yeah, that's how those answers come about, and then you'll obviously just combine them all together and write it in the form A plus BI. So guys, thanks a million for tuning in to today's Saturday session. I hope you found it useful. As I mentioned earlier, we do have a discount code that's offering 20% off the website until Sunday night at just before midnight. And the code that you need is complex20. And as I said, that will give you 20% off. We do run on a monthly subscription basis. So even for those of you who are in your Leaving Cert year, you don't need to be worrying about like a subscription for the full year. You can take it out now and pay for it for the next couple of months up until you're Leaving Cert, and then you can cancel it. So it's certainly worth having a look at. The entire algebra chapter is up there free of charge if you would like to get a taste for the videos that we have. And if you do have any other questions about today, as you would have seen throughout our presentation today, feel free to drop us any questions through our Instagram, and I look forward to talking to you all soon, and best of luck in your upcoming exams.